So this is the first way of solving systems of equations through an algebraic approach. And so I'm going to do them out of order, like I had mentioned before. I'm going to do 8.3 first, which is the first of two processes of algebra to solve these systems. And so the first process that we're going to talk about is solving systems of equations by substitution. And this is one that I find almost always works, and so that's why I choose to do it first. It's usually more reliable than this other process down here, but they're similar in that they're both algebraic approaches to solving systems of equations. In 8.1, we did the solving by graphing, which gave us those pictures. It gave us a conceptual understanding that systems of equations can be consistent when the two lines intersect, so this was consistent, and there was an x and a y that made both equations true. We could have the case where the line was actually the exact same line, and we said that that was a dependent system. And there would be an infinite number of solutions for that. Or the third case, when we put those two equations on the graph, we found that the two lines were actually running parallel to each other. And the description for that system was that that system was inconsistent. Oops, I almost wrote the wrong word there. Inconsistent. And there would be no solution for that. So that's an inconsistent system. Inconsistent, that's right. And there is no solution for that case. All right, so moving on to these processes that are all algebra in 8.3 and 8.2, we're going to have, some of the stuff that we've already done in this course used in our approach to this. So the general way to do this is to start with the two equations, and you're basically going to isolate one of the variables in one of the equations. Doesn't matter which one it is, and then take that value and sub it into the other equation. I think it's easier for me to show you how to do this rather than to tell you. And so these examples illustrate what we mean. So here we have two equations, and I like labeling them because this helps me explain what I'm doing. So I'm going to start with these two systems of the equations, and I notice that my second equation is already solved for y. And so what I'm going to do then is take and sub equation 2 into equation 1. So I'm going to sub in here. And so what that means is that where I see a y in that first equation, I'm actually going to write 3x. And so I would rewrite equation 1 as x plus 3x equaling 12. All I did was replace that y value there with the 3x here, right? I'm subbing it in. It's solving through substitution is the name of the game. So now that I've done this, I've made a new equation and I've eliminated one of my variables. I know how to solve these things now. So I would have x plus 3x. That would give me 4x equaling 12. And solving for x, I divide by 4 on both sides, and I get that x equals 3. Now, if we can remember about consistent systems, if we get a value for x, that means we're only halfway there. Now we have to solve for y. And so in this one, I could take this value of x equaling 3 and sub it into my equation 2. So when I do that, it looks something like this. So my equation 2 was that y equals 3 times x, but I'm saying that x equals 3. So this is what allows me to finish my solution to this system and say that y equals 9. If I put this back together, I could say that the ordered pair, the consistent system, has a unique solution of 3 for my x term and 9 for my y value. Let's try another one of that. I've got another one here that's a little bit more complicated. We'll do that one together. So I've got two equations. I'm going to call this equation 1 and this equation 2. And I'm going to start off. I see that equation 2 is already solved for y. And so what I can do with that is take equation 2 and sub it into equation 1, copying equation 1. And where I see that y, taking all of this and subbing in. Remember when I said we sub in with brackets? It's really important here. So we're going to sub into number 1 here. So I'm going to write out number 1 as 2x plus 3 times all of this 2x minus 7. Finish up the equation of number 1, writing equals 3. So again, now I've made an equation that I can solve for my x term. I'm going to have to use distributive property here. So I'd have 2x plus 6x minus 21 equaling 3. Keeping going on this one, I'd have 8x minus 21 equaling 3. Adding 21 to both sides, I get 8x equaling 24. And then finishing up dividing by 8, a lot of work, x equals 3. So now that x equals 3 on this, I'm able to take that and sub it into 2. So I'm going to take this up to the top here. I'm going to sub it into equation 2. So my equation 2 that I'd written here was y equals 2x, but I just said that x is 3. So 2 times 3 minus 7. And I can evaluate what y equals here. I'd have 6 minus 7, or y equals a negative 1. And rolling this all back together, I'd end up with an ordered pair to this consistent system. So they're all consistent systems. I'm going to drop writing that. My ordered pair would be 3 and 1, because x is 3 and y is 1. And those two values would satisfy both of the equations in this linear system of linear equations. Okay, so there's 2 more to do down here. If you want to go off on your own and do these ones, then that's cool. They're very similar to the ones that we did up above. But what we're going to do is start by numbering the equations. And again, because the second equation here is already solved for y, I'm going to take and sub that into my first equation. So writing out my first equation, I would write x minus 4x equaling 12. I took, and where I saw the y, I would sub in with that 4x. I didn't sub in with brackets here, and in all honesty, I don't always, unless it matters. If you find you're not subbing in with brackets when you ought to be, then put it in with brackets. Always a good idea. So in this case, it would be the same thing. I can solve for x here, so I'd have negative 3x. Those are like terms, so I can gather those up, equaling minus 12, divide by 3, and I'd get that x equals a negative 4. With this one, I'm halfway done on that. I could take that and sub it into any equation I want. I'm going to pick number 2 because it's already solved for y. So copying that, it would be y equals 4 times x, which is negative 4. I just evaluated that. So that gives me that y equals a negative 16. And in this one, then I could summarize my answer. It's a consistent system. There is a unique solution. There is a point where these 2 lines would touch each other. And thank goodness I didn't have to graph it because they're pretty big. At x equaling negative 4 and y equaling negative 16, these 2 lines would actually intersect each other. Those 2 values of negative 4 and negative 16 for x and y would make both of those equations true. One more here, and I'll try and be better with this subbing in with brackets. I'm going to take equation 2 and sub it into equation 1. So writing out equation 1 with, whoops, I did that wrong. Try that again. I was thinking it was a y. Okay, so subbing in my first, where I see the x in the first equation, I'm rewriting it with that instead. So 2 times 4y minus 2 subbed in with brackets, and then copy the rest of the equation. Now I have just a y in my equation. It doesn't matter whether you solve for x's or y's first, but you do have to track down both of these. So in solving this equation, a little distributive property, a little collecting like terms, a little isolating the variables, and solving for y. You can see here that we've got a y first. Doesn't matter which one you get, but now you have to track down the other variable. And so I'm going to take this and sub it into number 2. So that x equals 4 times 2 minus 2. I'd have x equaling 8 minus 2 or x equaling 6. And this is what rounds out my answer. I always give my answer with the x term and then the y term as an ordered pair, because this is literally a place on the graph where those two lines would intersect each other. So we've got 2 more to do, and then I think I'm going to break the video up a little bit here. So we'd have equation 1 and equation 2. In this case, neither of the equations has one of the variables isolated. It doesn't matter whether you pick on equation 1 or equation 2, but I'm going to change my equation 1 so that it's solved for x. If I did that and add 2y to both sides, I'd have x equaling 2y plus 5. This is now something that I can sub into equation 2. And so it has the same value. It would be the same line on the graph, doesn't matter how I organize it. But because I've isolated one of my variables, now I have that raw material to sub into my second equation. So rewriting my second equation, but using 2y plus 5 for where I see the x, plus y equaling 8, gives me a new equation that I can now solve for y. So a little distributive property, a little collecting like terms, a little isolating variables, and solving for y gives me that y equals a negative 1. That gives me the raw material to then sub in, and I can sub into any equation I want. I'm going to sub into my new number 1. So I'm going to sub into number 1, my reorganized number 1, so that x equals 2 times negative 1, because that's what y equals, plus 5. So x would equal a negative 2 plus 5, and then x would equal then a 3. And this is what gives me my final ordered pair information. I know that these two lines would intersect at x equaling 3 and y equaling negative 1. This is another consistent system. One last example before we get into the other two options. Again, these are all consistent systems. I have 2 equations here. Neither one of them is solved for one of the variables, so it doesn't matter which one you want to choose. Doesn't matter whether you solve for x or y first. Because there is a positive x sticking out here, I'm going to pick on that one. Oops. Subtracting 4y on both sides, I'd have an equation that x equals negative 4y plus 6. And this gives me something that I can sub into number 1, or the equation 1. So rewriting equation 1, I'd have 3 times negative 4y plus 6, and I sub in with brackets. Keep copying, negative y equaling 5. These like drawing of the arrows and stuff, sometimes I lose my train of thought and I need my instructions. And so that's why I do a bit of a roadmap here. I have as an equation with my distributive property negative 12y and positive 18. Copy that negative y and 5. A little collecting like terms. I'd have a negative 13y plus 18 equaling 5. A little reorganizing things. And solving for y. Y equals 1. And then I have to track down the other variable. I was about to give my answer, but I'm not done. I need to take this back to figure out the x variable. So I'm going to take that y equaling 1 and sub it into, what's that? My equation 2 there. So x would equal my reorganized number 2, right? X would equal negative 4 times 1, because that's what y equals, plus 6. So x would equal -4 plus 6, or x would equal a 2. And from all this, what I've determined is the point where these two lines would intersect. It is the unique solution for this system of linear equations.